Hello and welcome to Investigative Math. This is the third video in this series about confidence intervals, and in this video we're going to be talking about figuring out a confidence interval for means and for difference in population means. So, if you already have a decent amount of knowledge about confidence intervals or you've watched my last two videos, feel free to keep going. However, I am going to be assuming a decent amount of prior knowledge, so if you don't have that, make sure to go check out the previous videos, and then you can come back here when you feel like you're ready. Alright, so the first thing to do is we have to differentiate between two things. We have to differentiate between what are called z-intervals, or z-distributions, and t-intervals, or t-distributions. Okay? And there's just a couple rules about when you would use each one. The reason you have two different ones is because one accounts for more variability than the other. So for a z-interval, you use a z-interval anytime that you know the population standard deviation. Okay? Anytime that you know the population standard deviation. That's it. If you know it, then you can use a z-interval. Except for when you know the population standard deviation, but your sample size is less than 30. So that's an exception. That's something to think about. So if you know the standard deviation, you use a z-interval, but if it's less than 30, then you would have to use a t-interval. And of course, the only other possibility is that you don't know the standard deviation, in which case you would also use a t-interval. So that breaks it down, right? Your z-interval, you use it whenever you know your standard deviation and you're sampling more than 30. Or use a t-interval whenever you know the standard deviation but it's less than 30, or you just don't know the standard deviation at all. Okay, so now we're going to work on calculating a t-interval. So let's say we're given some information. We sample 50 people. Let's say we sample 50 people. And those 50 people, turns out that they have a mean of 25 and a sample standard deviation of 6. So this begs the question, are we going to be using a z-interval or a t-interval? So notice right here I wrote an s instead of a sigma. You may be thinking, oh, those are interchangeable, but there is actually a very important difference. An s represents the standard deviation of the things that you sampled, right? That's the standard deviation of these 50 individuals. Whereas the sigma would be the standard deviation of the whole population. So since we don't know the standard deviation of the whole population, we have to use a t-interval. Okay, so in the last video we figured out the formula for a confidence interval, right? It's our sample mean plus or minus our t critical value multiplied by the standard error of our distribution. So expanding this out a little bit, we don't know our t statistic. I'll show you how to calculate that later. But our standard error will just be our sample standard deviation divided by the square root of our sample size. Okay, yes, our sample standard deviation divided by the square root of our sample size. So let's see, our sample mean is 25. Once again, we don't know our t-statistic. We'll figure that out in a second. Our sample standard deviation is 6. And our our sample size is 50. Well, so how do I calculate this t-statistic? Well, first of all, I forgot to give you a piece of information. We're trying to create a 95% confidence interval. 95% confidence interval. That would have been important information to have. So basically, your t-statistic, right? If you've watched the previous videos, you'll recognize this graph, right? Here's our sample mean. This is, and this in here is 95% of our area, of our probability, right? Because we're trying to create a 95% confidence interval. If that seems weird, go watch the previous video. I explain it in more detail. So we're basically trying to find what is this value right here going to be? Well, we can use an inverse t distribution to do that because we have a t distribution and we're trying to find a value given a certain area to the left, right? If that's 95%, then these two together would be 5%. So that's 0.025. So the area to the left of this would be 0.975. And that's information we're going to need to know for our inverse t. So to get to that, you can go to your calculator. I know that on the 84, if you go to stat and then all the way to the right, it says test. It says test, but if you scroll down to the bottom or close to the bottom, wait, I said it wrong. If you go to distributions, there will be an inverse t distribution. I was thinking of something else. Sorry about that. Okay, you go to menu, statistics, distributions, and then you see number 6 says inverse t. So our area is 0.975. What's our degrees of freedom? Well, our degrees of freedom, this is a very easy formula. It's just your sample size minus 1. So that's just going to be, oh, gotta go down. It's going to be 49. So I click OK, and I get this t statistic of 2.01. So now I can use this to calculate my confidence interval, right? It's going to be that times 6 divided by the square root of 50. And then it's going to be 25 plus that for my high end, 25 minus that for my low end. So my confidence interval is everywhere from 23.3 to 26.7. So that's how you do it by hand, and it's important to know how to do it by hand because sometimes we'll ask questions where you can't necessarily use the program on the calculator. And so it's really good to know how to do it by hand. But I will show you how to do it on the calculator for the sake of saving time. If you go to menu and then statistics and then confidence intervals, you'll see number 2 is for a t interval. And this is actually the thing I was getting ahead of myself on the TI-84. If you go to stat and then all the way to the right, it says test. Well, if you scroll down, there's actually options for intervals. So that's where it is on the TI-84. Anyway, here's where it is on the Inspire. We don't have data, we just have the summary statistics. So we're going to click stats. And then we just type in the information we have, right? Our mean is 25, our sample standard deviation is 6, and our and our sample size is 50. And then if we want 95% confidence, click OK, and you see it gives us the exact same things that we had before. Okay, so that's not too bad. Yeah, that's not too bad. Obviously, if you saw this during a test, you would probably do it this way because it saves you from having to do the inverse t and all that stuff. But this is still, it's still not a replacement for actually learning the formula and learning the concept, because he will switch it up so that you can't just use that. So the next thing we're going to look at is how to find a confidence interval for the difference in means. And I'll warn you that some of these formulas that we're about to go into are a little bit more complicated. I don't know if he would ever try to make you use these formulas, but at the end I will show you the way to do it on the calculator once again. So let's say we have two populations. We have P1 and P2, right? And from P1 we took a sample of 50 people. Sorry, for P1 we have a mean of 50 taken from a sample of 60. And then a standard deviation of 5, sample standard deviation of 5. And then from our second one, we have a mean of 30 out of a sample of 100 people, and this has a standard deviation of 3. So we still use the same formula, right? Confidence interval is our sample mean plus our t-statistic multiplied by the standard error, except this is a little bit weird because we have two sample means. We would have two standard errors if we were to calculate it. So what we actually have to do, instead of finding a confidence interval for P1 and P2, you find a confidence interval for P1 minus P2. So what is this distribution going to look like? So the mean of this, right, would just be 50 minus 30. The standard error is a little bit weird, but here's how you do it. There's a formula with a standard error, and it's often called the Pythagorean theorem of statistics. And it's, for some reason that I'm not entirely sure about, you can add the squares of standard errors, but you can't just add the standard errors on their own. It's a little bit weird, um, but um, but we're just gonna take their word for it for now. So if I wanted to find the standard error of this combination of 1 minus 2, right? Population 1 minus population 2, it's going to be the square root of the standard error of 1 squared plus the standard error of 2 squared. And no, this is not a typo. I'm finding the difference in these means, and yet I'm still adding the squares of their standard errors. That's not a typo. That's how it's supposed to be. Okay, so how can we do this? Well, the standard error of our first one, well, standard error is just standard deviation divided by the square root of n. So we could even say that standard error squared is s squared over n. So actually, I'm going to write it that way. Yes, so s1 squared would be 5 squared over 60, and s2 squared would be 3 squared divided by 100. So hopefully you're following along with your calculator. And let's see what we get. So that's 25 over 60 and 9 over 100. And then we want the square root of that. So you get a standard error of 0.7118. Okay, this is the standard error that we're going to use in this right here. Okay. Now the final thing to do is calculate our t-statistic. Calculate our t-statistic. Which, okay, I keep forgetting to do this. If I forget in future videos, just assume I'm doing 95% confidence. Yeah. So we're dealing with 95% confidence, and we're trying to find this t-statistic. Well, it's a little bit trickier this time around because of the way stats works. It's not going to be simple, and this is the formula I was talking about before we even started. That's pretty complicated. There's kind of a complicated formula for finding the degrees of freedom of this, which of course you would have to use the inverse t distribution. So you're still going to use an area of 0.975. Right? And if you're not familiar with what I'm talking about with this inverse t distribution, go watch some of my previous videos. I don't want to go too in depth this time around. Yeah, right. So we're still going to use an area of 0.975, but the degrees of freedom formula is pretty complicated, and this is why I'm going to show you the way to do it on a calculator later on. So here's the degrees of freedom formula. Let A equal the standard deviation of 1, sorry, the standard error of 1 squared. So it would be like S1 squared over N1. And let B equal S2 squared over N2. So basically, A is the square, A is the standard error squared of population 1, and B is the square of the standard error of population 2. You can think of it that way. Then the degrees of freedom, and don't worry about memorizing this formula. If you really want to, you can type it in the notes section on your calculator. But I highly doubt he'll make you memorize this. It's A plus B squared, all divided by A squared over N minus 1. Sorry, over N1 minus 1. Let me just scroll down a little bit, actually. I'm running out of space. Let me rewrite this. Yes, over A squared over N1 minus 1 plus B squared over N2 minus 1. This is our degrees of freedom formula for a difference in population means. I'm not gonna lie, it's kind of a doozy, and it's a long formula. And if he makes you memorize it, then I guess it's not way too difficult to memorize, but it is still a lot. That's why I'm going to show you how to do it on the calculator later. So we can actually find this, right? Just because it's difficult doesn't mean we're just not going to do it. So the degrees of freedom of this, right? Well, let's find A and B first. What are A and B? Well, we figured it out over here, right? A is just the square of the standard error, which we found out was S squared over N. So this is going to be 25 over 60 and b will equal 9 over 100. So our degrees of freedom calculation will be 25 over 60 plus 9 over 100 squared, right? Over a squared, so 25 over 60 squared over n1 minus 1, which is 59, plus 9 over 100 squared, all divided by 99, right? 100 minus 1. So it's a pretty long formula. Let's figure out what this is actually equal to. Hopefully you're following along with your calculator. So it's going to be 25 over 60 plus 9 over 100 squared over, make sure I'm typing this right, because if I mess this up, it's going to throw a wrench in pretty much the rest of it, over 25 over 60 squared over 59 plus 9 over 100. Yes, I know I could just write 0.09, but I'm trying to show the whole thing just for the sake of clarity. All divided by 99. And so you get 84.88 degrees of freedom. And yes, that is a non-integer degree of freedom. You might be asking, what does that even mean? I'm honestly not sure. I'm gonna have to look into that. I might even make a video going more in depth on this formula if people want that. But it is kind of interesting. But this is the degrees of freedom we're going to use. So now we can finally calculate our t-statistic. So we go to Menu, Statistics, Distributions, Inverse t. Our area is 0.975. Our degrees of freedom is 84.88. And so we get a t-statistic of 1.9883. So I'm going to go ahead and delete that. Right? Which means our margin of error, right? This right here is our margin of error, is equal to that t-statistic we calculated, or t-critical value, multiplied by our standard error, which we calculated before. It's going to be that times that, which gives us 1.415. Okay. And now all we have to do to find our confidence interval is take our sample mean, right, which is 20. And so our confidence interval will just be 20 plus or minus that 1.415. So 20 minus that on the low end, 20 plus that on the high end. So our confidence interval, we're 95% sure that the true difference in these means are from 18.6 to 21.4. So that is a lot of work. That is a lot of work. So I'm going to show you how to do it on the calculator now. I decided I would include that just in case there were some people that were curious about it. But in all seriousness, I looked up this formula for degrees of freedom as I was watching the video, and I made it pretty well without this formula. But just like to future-proof the videos as much as I can, and maybe someone was really interested in that. All right, so let's go. Statistics, confidence intervals, and then we're going to do a 2-sample t interval. There we go. We don't have data, we have summary statistics, so I'm going to click that. Our sample mean for number 1 is 50, and then 5, and then 60. Did I use those? Yes. And then 30, and 3, and 100, 95% confidence. And depending on the calculator you have, you may have this option for pooled. For right now, we're going to assume no. We're gonna assume no. I'll go into more pooled statistics whenever we talk about statistical tests. But for right now, if you're not sure if it's pooled, you want to put no just as a safer bet. So I click OK, and you notice if you scroll up a little bit, you get the exact same interval as before, and noticeably quicker, which is good. So that's how you find these intervals to calculate the difference between population means. It is quite long to do it by hand, like I've said, but if you know how to do it on the calculator, it's much quicker. This is a formula that you probably won't have to memorize. However, this formula over here is a really good one to memorize. The standard error of the difference, or the sum of two distributions, is the square root of the sum of the squares. That's a really good one to memorize. And plus, if you just call it the Pythagorean theorem of statistics, right, then it's a lot easier to remember as well. So Hopefully, over the course of this video, it's kind of a long video, hopefully you learned something. If you did, make sure to leave a like and subscribe. If you think I made a mistake or want me to go into something in more detail, don't be afraid to leave a comment, and I will see you in the next video. See you next time.